This is Pre-Calculus 12, Chapter 5.7. We're going to be looking at solving logarithmic and exponential equations. Since log and exponential functions are inverses of each other, sometimes it's easier to use the inverse function to solve the problem, especially if you are doing it algebraically. And the difference this time is we always check for extraneous values. Let's look at some simple examples. Log base 4 of x plus log base 4 of 3x equals 2. Let's use the log laws here. Since we're adding, that means we're multiplying the parameters. Log base 4 of 3x squared equals log base 4 of 4 to the power of 2. Now we can exponentiate both sides with base 4. So this is really 4 log base 4 of 3x squared equals 4 to the power of log base 4 of 4 squared. These two operations cancel out. Normally we skip this step, but I'm demonstrating what's actually going on behind the scenes. So now we have 3x squared equals 4 squared, that's 16. So x squared equals 16 over 3. And x equals plus or minus 4 over square root 3. It's best to rationalize the denominator, so we need to multiply by root 3 over root 3. And we get plus or minus 4 root 3 over 3. And negative 4 root 3 over 3 is extraneous. And we know this because if we look at the original equation, the domain is x is greater than 0. This is negative, so it's not greater than 0, therefore it's extraneous. Let's look at another problem. We have 5x equals 72. So what we want to do is use the log laws, take the log of both sides. Log 5x equals log 72. We use the log law to bring the exponent out front. X log 5 equals log 72. And now x is simply log 72 over log 5. And we need to take the log because there's no common base. And on the test, leave answer. In this form if algebraic. Round only when asked to. Okay, we have some more complicated problems. Log base 2 of x minus 4 in brackets plus log base 2 of x plus 3 in brackets minus log base 2 of x plus 1 in brackets equals 3. And we take the most restrictive domain. X is greater than 4, x is greater than negative 3, x is greater than negative 1. So x is greater than 4. This is the most restrictive. And the way we do this is to check the overlap. Okay, let's combine this into a single log. Log base 2 of x minus 4 times x plus 3 over x plus 1. and that equals 3. But let's convert this to a log base 2. We use the same base, and we use that as the power. Okay, now we can remove the logs. And we have x minus 4, x plus 3. That's 8. And we're multiplying by x plus 1. Now we need to expand everything. X squared minus 4x plus 3x, that's negative x. Negative 4 times 3, it's negative 12. And we have 8x plus 8. Let's move everything over to the left-hand side. X squared. This becomes negative 8x, so negative 9x. This becomes negative 8, so we have negative 20 equals 0. It's hard to tell if this is factorable, so it's best to use the discriminant. B squared minus 4ac, so that's negative 9 squared minus 4 times 1 times negative 20. This equals 81 plus, this is 80. This is 161. 161 is not a perfect square. This means we should use the quadratic formula. So x equals minus b, that's minus negative 9, plus or minus square root. We've already calculated the discriminant, so let's plug that in. And 2 times a, that's just 2 times 1. Simplify this a bit. 9 plus or minus square root 161 over 2. We said x is greater than 4. Well, square root 161, the closest is 169 equals 13 squared. So that means 9 minus a bigger number is going to be less than 0, which is less than 4. So 9 minus square root 161 over 2 is extraneous. And 9 plus root 161 over 2 is our solution. Let's look at another example. Again, we do not have a common base, but we can still solve this algebraically. We take the log of both sides. The exponent comes out front. Now we expand. X log 5 minus log 5, x log 3, plus 2 log 3. Bring all the x's to one side. We have x log 5 minus x log 3. And we have log 5 plus. Bring the 2 inside. So that's 3 squared, that's 9. Factor out an x. Log 5 minus log 3 equals, this is addition. That means we multiply the parameters. That's log 45. and x equals log 45. This is subtraction, so that must mean it's division. So we're dividing by log 5 over 3. And that's our final answer. Okay, so to do this stuff, have your log and exponential rules handy, but if you've worked with them enough, I think you'll memorize them. And the key to solving is to get a single log on both sides. Or a single exponential on both sides. Then use the inverse function. To solve. So here we had exponentials, and we just took the log of both sides. Here we had logs that we had to simplify, and then we wanted to get a log on the other side. Here, again, we had a log on one side, and we need to convert this to a log on the other side, and then use the inverse operation. And again here, we use the inverse operation to get rid of the logs. Here we just kept the logs in our answer. And that completes this lesson.